Hi, my name is Noson Yanofsky. We're doing the Outer Limits of Reasoning, that's the class, and we're doing Chapter 6, which is about, let's just put it in context. Chapter 5 was about problems, computer problems, that took a long time to solve, millions and trillions of centuries. We saw that. Okay, but in Chapter 6 we're going to talk about problems that computers cannot solve. They just cannot solve at all. And we're going to deal with these issues. Okay, not that they can't solve in a long time, they just can't solve. So there are a lot of things that a computer can't solve that we know of, we have an intuition of. For example, a computer cannot tell if a painting is beautiful or not, or if a painting is going to be a bestseller, or whatever, a piece of art. A computer can tell what certain people like. In other words, they can figure out what certain people like, and they can tell you, oh, certain people like this, okay? Things that they have common patterns of. But it can't tell you what's beautiful or what's a piece of art or something like that. Now, it's a little bit more complicated than that. So the idea is as follows. The guy who's considered the greatest artist of all time, or the greatest artist nowadays, is Van Gogh. In his lifetime, Van Gogh was not able to sell one painting of his time. So the question is as follows. If you were to get a computer to predict beautiful paintings, should you get a connoisseur from his generation while he was alive, or from our generation, to help you program that? That's what I'm trying to say. It's kind of a subjective thing, what's a beautiful painting. When he was alive, his paintings weren't considered worth anything. When he was dead, or 50 years after he died, everything that he sneezed on a tissue, they think is an amazing thing. So, but anyways, that's beyond the ability of a computer. Now, let's talk about other things. So that's painting. Another thing is beauty. There's no way in the world a computer is going to be able to tell what's beautiful, what's not beautiful. There's no way in the world a computer can tell what's a moral action. Okay, what's the right thing to do at a right time. And again, a computer can be programmed to be told what is moral by some experts, but that's not telling what's a moral action and what's not. And in fact, I told you once, I think that, I don't know, a third of science fiction movies are about time travel. I'll say a third of science fiction movies are also about computers taking over and doing evil things. But fine. Now, in all these things, in art and beauty and morality, you could say they're subjective things. They're subjective questions. Whether or not something's beautiful, well, it depends on who's asking. Okay, whether or not an action is moral or not, that depends on who you are. Some people think some things are moral, people think things are not. So those are subjective, depends on who you ask. So you could say, oh, you know what, a computer is not good at subjective things. That's true. Okay, but in this class we're going to see objective things that a computer cannot answer. Okay, objective things that a computer cannot answer. Okay, so that's a little bit of an interesting thing. Okay, now there are some objective things also that computers cannot answer, like tomorrow's lottery number. Okay, I cannot program a computer to tell me what tomorrow's lottery number is. It's just impossible. Okay, because there's too many variables going on. I can't even tell a computer to figure out what the weather will be in 3 days. Maybe a little, it can give me a good prediction for tomorrow or the day after, but 3 days already is pretty far. Computers aren't very good at it. I cannot get a computer to predict what tomorrow's stock prices will be, or next week's stock prices. If I would be a very rich man. Okay? Now, those things are objective. What the price of IBM or Apple will be in a week, there's an objective answer to that. But the problem with that is that's way too complicated. You need too many, you have to worry about too many inputs. You have to worry about too many things. You know, this worker said this buyer decided to buy that. Too many things to worry about. In terms of the weather, there's too many variables going on there, so it's too complicated. So there is an objective thing. There are objective answers. Computers can't do it, but it more can't do it because of what we learned in last chapter. In last chapter, we saw that certain things are just too big and complicated to be able to deal with. Okay, here we're going to deal with questions that are objective. There are objective answers to them, and yet it's not that it's too complicated. It's something else, and it's something else that we know and love from this class, self-reference. So we'll see that. Okay, just another thing, computers can't figure out who will fall in love with who. That takes too much neurology. The brains are just too complicated to figure out. Computers can't figure out tomorrow's weather. There's something we're going to see when we talk about Chapter 7. It's called the butterfly effect. Little butterflies flipping their wings could cause major changes in the weather, so we're not going to deal with that. Again, since we can't keep up with all the butterflies or all the people going like this, so too we can't keep up, we can't describe these things. Okay, by the way, there are other things that computers are not good in. Raising a child. You wouldn't want a computer to raise a child. Again, moral questions. You don't want to make a computer give a computer a gun or a weapon, simply because they're not good with moral questions and they always turn out things. I just made a list of all the movies that have this. War Games, 2001: A Space Odyssey, Tron, Terminator, Matrix, Westworld, iRobot. Okay, all these types of things. You don't want to give computers things. But there are other things that computers are not good at. Here's one. Computers are very good at chess playing. In fact, 99.99% of people on planet Earth can be beaten by a typical game on your phone. Okay? Now that's different than 30 years ago. 30 years ago there were chess games, but human beings can beat them. But nowadays pretty much most human beings cannot beat a typical chess player. So that's pretty good. So computers are good at chess. In contrast, computers are not very good at playing tennis. Okay? It's hard to play tennis. I mean, they have to follow the ball, quick paces, not too quick, whatever. So that leads one to believe that tennis is harder than chess, which I think is true. Anyways, that's from somebody who can't play tennis. Okay, but I promise you, in 20 years, there will be computers playing tennis, and they will be better than chess play. They'll be better than any human being around. So that's that joke about tennis being harder than chess. Well, that's not going to last very much longer. As computers get better and better at robotics, we'll be able to do that. Okay. Something else that computers were not good at, but they're getting much, much better, and that's voice recognition. They're understanding what people are talking about. And this was really brought home 2 or 3 years ago, or a while ago, when Watson was playing on Jeopardy, and Watson beat every human person, and supposedly it just followed voice recognition. It somehow understood the questions. So Watson, it's just an IBM thing that did. So again, we'll talk about this. We're looking for objective problems, which have objective solutions, which is not too complicated, which we saw last. The problems we're going to be talking about in this class are objective problems. They have objective answers. They're not that it's too complicated, like we saw problems like the traveling salesman in last chapter. Okay, so they're not too complicated questions, and computers will not be able to do that. Okay, so what is an example? We're going to see many examples of these types of problems that computers, objective problems that computers cannot answer. But I'd like to tell you one of them, just to foreshadow a little about what we're going to do. It's called the halting problem. It's telling when a computer will halt. Okay, telling if a computer will halt. Okay, so you all know when the computer is somehow in an infinite loop, it's not breaking out, okay, and the computer somehow gets stuck, okay, and on top of the computer it says not responding or something like that, and you have to press Control-Alt-Delete and reboot or start it up. The question is, we have such amazing computers doing amazing things. We have such amazing operating systems running the computer. Why can't the computer just say, look, oh, it's in an infinite loop, stop? And the answer is, in other words, we have computers that can figure out this and figure out that. Why can't they figure out whether a program will halt or not halt? And we're going to get into this more and more as we go on. And the answer is because computers cannot do that. Okay, so telling you guys don't know what the blue screen of death. That was something that computers used to, when they were in an infinite loop, they would get into a blue screen of death. So we're going to go into that deep. But the idea is as follows. Whether a computer will stop or will not stop is an objective question. Okay? And yet a computer cannot answer it. Okay, so let's get started. We're going to build up to this. So one of the things that we do in this class is we're not going to write programs. Okay, this is not a programming class. This is not a class made. This is made for any student, not necessarily for a computer student. So we're not going to write programs, but we are going to learn how to read a program. It's very important to learn how to read a program. We're going to learn the nitty-gritty details of how a computer works, so that we can learn how computers work and how they get stuck in their loops. So we're going to do that. Okay. And before we do that, we have to go through these 4 words: algorithm, program, computer, and machine. Okay. Now, we're going to use these 4 words interchangeably in the following sense, but let's go through what each one of those words mean. Okay. An algorithm is a set of ideas of how to do things. Okay. When you wash your hair in the morning, it says rinse, lather. No, how does it go? Wet, rinse, and lather, something like that. No, wet, lather, and rinse. And then it says repeat. So that's an algorithm of how to wash your hair. You first wash your hair, then you put in shampoo, lather it all up, etc., and then repeat, do it again. Okay, so that's an algorithm. It's an idea of what to do. Okay, how to cook something. Well, you pour the water in, you do this, you do that, etc., etc. Okay, turn the fire on, put the spaghetti in, etc., etc. Those are algorithms. There are algorithms. There's algorithms how to do everything in the world. How to pass this class. Study, read the book, etc., etc. Okay, as opposed to that, a program is something that only a computer can understand. It's an exact description of an algorithm. Okay, so again, algorithms are not exact. For example, tells you put the shampoo in your hair. Should you put it in your right hand? Should you put it in your left hand? Should you pour the shampoo at a 90-degree angle, at a 45-degree angle, at a 46-degree angle? Well, if you're just giving the idea, it doesn't really matter. But if you're writing a program for it, somehow every single thing has to be expressed exactly. So a program is an exact description of an algorithm. Okay, a computer is something that runs programs. Okay, computers are things that run programs, and then a computer is a special type of machine. So we English speakers use those 4 words to describe different things, but they're pretty much the same thing. And what we're going to say is that an algorithm cannot solve this problem. We're going to talk about certain problems, and we're going to say an algorithm cannot solve it. There's no program for it. There's no computer that can solve it. There's no machine that can solve it. We're going to use these words interchangeably, but I want you to get a feeling that what each one of these words are, and not just see them. So we're going to use these phrases interchangeably. Okay, great. So now, since one of our goals is to learn how to write a program, then we're going to write programs. Okay, I'm sorry, one of our goals is to read programs. We're going to have to do certain things about reading programs. So programs are about variables. They're changing variables. And so let me just show you. We're going to deal with a programming language. It's not a complicated programming language. There's very few commands. You don't have to get nervous, oh my god, I can't do programs, whatever, because it's a little thing. It doesn't have a name, I just made it up, but it's something like this. So you're going to have variables, okay? And variables are places in the memory that can store we're only going to deal with whole numbers. Actually, we're only even going to deal with positive whole numbers, so it can store a number. So the variable could store the number 35. Okay, but then you can change the variable and it can store the number 52. Whatever. Each variable at any one time can store whatever it has. Okay, and then you could have two variables. Okay, so you could have a variable x and a variable y, and the variable y might have the number 13 in it. Okay, and then you could have another variable called z, and z could have nothing in it. And then there could be a line that says as follows: z is equal to x plus y. Okay, and so it will look at the present value of x, it will look at the present value of y. 52 plus 13 is 65, and I'll put it in there, 65. Now, that's about it, okay? But the main thing is when you're reading such things, this is what a typical line on your program will be. When you read such things, usually you read from left to right, but here you're going to read from right to left. You're going to figure out what's there, and then you're going to put that value into that variable, okay, into that memory box. Okay, and we're going to do this. Now, you could have something like this also. Z is equal to z plus 1. Okay, z is equal to z plus 1. So watch what we're doing. Again, we're reading from right to left. Z plus 1 is 66. 65 plus 1 is 66. Put that in there. So it's going to do, again, a variable can only hold one value at a time. It was 65 and now it's 66. Okay, and then you're going to have x is equal to x plus 3 times y. So this is a little bit more complicated. 52 plus 3 times 13. 3 times 13 is 39. 52 plus 39 is 90, 50. 52 plus 39 is, there's a 1 over here, it's going to be 91. Okay, so look what it says. 52 plus 3 times 13 is 39, and so it's going to put 91 in here. Okay, and we're going to go on doing this over and over and over. Okay, so rather than going through showing you programs, what I did in the book, in the handbook, right over here, is I give you 18 different programs. It says Programs for Computer Impossibilities. This is the chapter, and we're going to go through 18 different programs. Most of them are pretty easy. Most of them they get progressively harder, and they're each one, the new development is going to teach us something new. Okay, and so we're going to do most of them. We're going to do them one after the other. Okay, let me erase the board and write up 2 or 3. Okay, so we're going to start with this program. Look what happens. There's a few extra things. Look at this. X is equal to question mark. Computers don't only manipulate data, they have to input data. So what happens? You put your card into an ATM machine. The computer stops and asks you for your password. You have to input things. You have to input information. So this is the way we write it. We say as follows. X is equal to question mark. Question mark means stop. Ask the user for a number. Okay? So let's say the user, so there's going to be a memory box called X, and let's say the user enters the number 19. Okay? Now, watch the way we read this program. We read from top to bottom and from right to left. So X is equal to question mark. That means stop, let the user enter a number. X is equal to X plus 1. So X plus 1 is 19, plus 1 is 20. Put it back into X. Great. Now we're going to do it again. X is equal to X plus 1. 20, add 1 to that is 21. Put it back into X. Great. X is equal to X plus 1. 21 plus 1 is 22. Put it back into there is 22. Okay. Then, not only do we have to input information, we have to output information. So think about this as a piece of paper. It's going to output 22. Stop. Program stops. Great. Okay. So now we know about this when you input something and you output something. Those are things called functions. So we write functions as follows. I'm going to write as follows. This program does this function. When I input 19, that's the input, I get out 22. Great. What happens if I input something else? For example, again, let's say I input 53. Well, great. The user inputs 53, then it's going to increment 1, then it's going to increment 1, then it's going to increment 1, so it's going to go to 54, then it's going to go to 55, then it's going to go to 56, okay, then it's going to print 56. So, if the user inputs 53, then the program will output 56. Okay? And we can go on doing this again and again. Okay? If I input 129, no, we did 9 already, 127, then what's going to happen is this line is going to input it to increase it to 128, this line is going to increase it to 129, this line is going to increase it to 130, and the output will be 130, and so we write as follows. F of 127 is equal to 130. So far, so good. Okay, so we did 3 practice examples. Now, question, what is this function that the program does? Every program that we're going to see does a function. We practice a little on some inputs, but now we can tell exactly what the function will be. And the function is as follows. F of x is equal to x plus 3. That is the function that this program does. Great. Now that's a pretty simple program, but we're going to go on to more and more complicated programs as we go on. Okay, so let's erase this because we don't need it, and we're going to need all the room that we can for that. Okay. Now in your handout you should write down that this program, this is what this does. F of x is equal to x plus 3. Okay? It takes whatever the input is and adds 3 to it. It adds 3 one at a time. Great. Now let's do this. This is a program with 2 inputs. So let's write the 2 inputs here. You're going to have a memory place for x. You're going to have a memory place for y. I'm sorry, it's going to have 2 memory places. There's only 1 input. Okay, so let's go through how this program does. X is equal to question mark. Let's say the user enters 53. It's a good number, why not? Okay. Now here, this line doesn't mean stop and wait for the user. That just means put y is equal to 10. So put a 10 over there. Great. Okay. Now let's go through it. X is equal to x plus 1. So this is 53. It's going to go to 54. Y is equal to y minus 1. This was 10. This goes down to 9. Now, I told you that programs read from right to left and they go from top to bottom. Not always do they go from top to bottom. So here's what's called a conditional branch. Conditional branch. Okay. There's a condition, and it might go someplace else. Usually programs go from top to bottom, but it might go someplace else. Look what it says. If y is greater than 0, y is 9. 9 is greater than 0, go to a. That's a. Okay, so this is called a label. This line is a label, and so we go back here. Okay, now we're going to see later on, sometimes it doesn't, but we're going to go back here and we're going to do the same thing over again. This is the beginning of what's called a loop. We're doing a loop. We're doing something over and over. Okay, so let's go through it. X is equal to x plus 1. That was a 54. Now it goes to 55. Y is equal to y minus 1. This is an 8. If y is more than 0, 8 is more than 0. So we go back to a and we do it again. Okay, this goes to 56. This goes to 7. 7 is more than 0, so we do it again. This is 57. This is 6. Okay, and we keep on going over and over. 6 is more than 0, so we do it again. This becomes 58. This becomes 5. Okay, and we keep on doing this over and over. Let's just do it quickly. So this becomes 59, and this becomes 4. This becomes 60. This becomes 3. This becomes 61. This becomes 2. This becomes 62. This becomes 1. 1 is more than 0, so we go on and do it again. This becomes 63. I want to erase that. It's still in the memory box. It just ran out of a little room. This becomes 63, and this becomes 0. Okay, now look what happens. X is equal, now it's as follows. We're up to here. We just went, 63 went up. We incremented 62 to 63. We decremented y. We came down here. And now look what it says. If y is more than 0, is 0 more than 0? No, it's not. 0 is not more than 0. And so we don't listen to this branch operation. We don't do the branch. We don't go back up. We just go to the next line. So again, programs go from top to bottom except if there's a branch. So look what it says. Print out, here's a piece of paper, print out 63. Stop. Great. Let's see what happened here. The user entered 53 and the computer outputted 63. Okay? Great. Now, what would happen if I inputted something else? We're doing this very slow and carefully so that everyone gets it. If I inputted 127, okay, well, again, let's see what happened. Y would equal to 10 again, okay, and so this would go to 128, and this would go to 9, okay. 9 is more than 0, so we would do it again. 129, this would go to 8. 8 is more than 0, etc., etc. Okay? All these would go out till you get to 137, and this would go all the way down to 0. Okay? If y is more than 0, 0 is not more than 0, so we don't do this again. We'll do this loop 10 times. Okay, and we'll get out 137. So let's go through this. The user inputted 127. The output was 137. So let's do this. Let's remember. We inputted 52. We inputted 53. We got out 63. We inputted 127. We got out 137. Okay, let's just go through. How is this program doing? What this program is doing this 10 times. And every time it increases x, it decreases y until y is empty. Okay, okay, great. Now, let's say the user entered 291. Then the output would be, again, we would do this loop 10 times. If you input 291, the output would be 301. Okay, so let's write that down. F of 291 equals 301. Now, these were 3 warm-up exercises, in a particular if the user enters these things. But now let's do the general. What's the answer? This function is f of x is equal to x plus 10. Okay? Because it does this loop 10 times. And each time it does this loop, it increments by 1. Stop. Question. Don't change this on your notes. What happens if I made this not a 10, but a 17? Then it would do this loop not 10 times, but 17 times. Okay? It would do this loop 17. It would start off at 17, then it would go down to 16, then down to 15, then down to 14, down to 3, down to 2, down to 1, down to 0. Then it would stop doing it. And it would go like that. Okay? In that case, don't write this on your notes because you're going to ruin your notes. It would be f of x is equal to x plus 17. You would do this little loop 17 times, each time incrementing by 1. Okay? Great. Let's not change that yet. Okay, so we did number 2. Now let's do number 3. Number 3 is slightly different. Okay. It's almost exactly the same, except instead of this being a plus, this is a minus. Okay, so let's see what's going to happen here. It's almost exactly the same, but we're learning new programming concepts. Let's see what would happen here. Okay, y is equal to 10, x is equal to x minus 1, y is equal to y minus 1. So not only are you decrementing, decreasing y, but you're also decreasing x. So let's see. If I entered the number 17, what would happen? So you stop, the user asks for a number, it's 17. Y is equal to 10, so we're going to put 10 over here. X is equal to x minus 1, this was 17, now it goes down to 16. Y is equal to y minus 1, this goes down to 9. If y is more than 0, 9 is more than 0, so we go on and do it again. So this becomes 15, this becomes 8. If y is more than 0, we do it again. 8 is more than 0, so we do it again. This becomes 14, this becomes 7, ... Each time we do this loop, we do x minus 1, y minus 1. What's going to happen at the end? Well, this is going to go down all the way till 8, and this is going to go all the way to 1. Okay? If 1 is more than 0, yes, 1 is more than 0, so then do it again. This is going to be a 7, and this is going to be a 0. Okay? If y is more than 0, 0 is not more than 0, so it's going to not do this. It's going to go to the next line. It's going to print out 7. Okay? So that's a nice program. I inputted, let's just see what this is. If the user inputs, or if the program gets inputted, I don't even think that's a word, 17, the program will output a 7. Okay? Let's do some more. Let's say the user enters the number 59. What will be outputted in 59? You could stop the computer and try to figure it out yourself, but basically it's going to go through this 10 times. Each time it's going to decrement, decrease 59 one time. 59 to 58 to 57 to 56, etc., until you're going to get 49. Okay, and so we're going to do this. F of 59 is equal to 49. Okay, that's very nice. Next, if I inputted 123, it would output 113. Because, again, why? Because it's going to do this loop 10 times. Each time it subtracts 1. Okay, let's finish this off. What does this program do? F of x is equal to x minus 10. Okay, so that's very nice. That's program number 3. Great. Let's do number 4. Number 4 is almost the same. Let's go number 4. I'm going through this sheet very carefully. Number 4. Okay. Here we had increment x just like before, but here instead of y is greater than 10, this becomes y is less than 10. Instead of y is greater than 0, this is y is less than 10. Okay? Okay? So we made one little change, and this is why programming is hard, because if you make one little change, it changes everything. Okay, so that's a very important point. Okay, so great. So let's look at this program and let's do this program. Okay, you know what? I'm going to let you do it for a second. Okay, let's say you entered 27. Okay, let's say the user enters 27 and y is 10. Now let's tell me what gets outputted. Okay, so what does this program do? Let's pick a typical thing, 27. So let's do it. The computer stops, waits for the user to enter a number. The user enters 27. Automatically is y is equal to 10, x is equal to x plus 1. So this 27 goes to 28. Y is equal to y minus 1. This becomes a 9. If y is less than 10, 9 is less than 10, go to A. So we're going to do A, go to the end. So this is going to become 29. This is going to become 8. Okay? 8 is less than 10, so it's going to do it again. So this is going to go to 30. This is going to go to 7. Do it again, do it again, do it again. So this is going to go till 37. This is going to go down till 0. Now let's see. Is 0 less than 10? Yes, 0 is less than 10, so it's going to do it again. This is going to go to 38. This is going to go to -1. Why is 0 minus 1 is -1. I'm going to do this again and again and again. Okay? Let's do it 10 more times. So this is going to go till 47. And this is going to go till -10. Is -10 less than 10? Yes, it is. So what's going to happen? Okay? And the answer is, it's going to do it again and again and again. Question, when will it get to this line, print x? Question, what is the output for this program? Answer, there is no output for this program. This program will just go around this loop over and over and over again forever. It's in an infinite loop. Okay, because any number here is less than 10. We started off with 10 and we went down, so any number is less than 10. So the way we write this is as follows. We say f of 27, that's the function that this does, is up arrow. Up arrow means it's an infinite loop, it's going to go on forever. Okay? Good. What happens if I inputted 59? Okay? Well, the same thing is going to happen again and again and again. We're going to start off y is equal to 10. We're going to do this again and again and again. And again, up arrow means there's no output. It just stays in the air. That's the way to think of it. Okay? In particular, if I did f of x, whatever the person inputs, it goes into an infinite loop. And we're done. Okay? So this is our first example of a program. It's a totally legitimate program, but it goes into an infinite loop. Okay, great. Let's do number 5. Number 5 is a little bit more interesting, but it's similar to this. So let's write up number 5. First we want to erase this. You know what? We can let's write both of them. Let's do number 5. It goes x equals question mark, y equals question mark. If y is equal to 0, go to b. Okay? A, that's a label. X equals x plus 1. Y equals y minus 1. If y is more than 0, go to A, B. Print x. Stop. Okay. That's a go-to. Okay. Now, this is an interesting problem. Again, every new problem we're going to do, we're going to add another new interesting idea about programming, and we'll get a better insight into how programming works. This has not one input, but 2 inputs. So let's do it. You're going to have x and y. So we had 2 variables before, but we have 2 inputs. Let's go through this. So the computer's going to stop, ask the user for a number. So if the user enters 27 here, and if the user enters y is equal to 7 over here, let's see what's going to happen. Okay? If y is equal to 0, no, it's not equal to 0. No, it's not equal to 0. X is equal to x plus 1, so this becomes 28. Y is equal to y minus 1, this becomes 6. If y is more than 0, go to A. That's exactly here. That's a loop. By the way, this program, this part of the program, looks very, very similar to what we had before. Okay. X is equal to x plus 1, so this becomes 29. This becomes 5. 5 is more than 0, so we do it again. 34. Again, 31. 3. Again, 3 is more than 0, so we do it again. 32. 2. Again, 33. 1. 1 is more than 0, so we go to it again. 34. 0. Okay, great. Now, we did y is equal to y minus 1, that's 0. So, is 0 more than 0? No, it's not. So we print x, and the output is 34. So let's just write up the output. If the input is 27, but I'm now inputting more than one thing, I'm inputting two things, 27 and 7. Okay, if you input 27 and 7, the output will be 34. Okay, why? Basically because I did this loop 7 times. So I added, each time I added 1, 27 plus 7 is 34. Great, let's do another one. We'll do it quickly. If I did 51 and I did 13, let's see what would happen here. I don't want to erase this, so we don't have to go through this so good. But what would happen is I would increment 51 to 52, 53, 54, 55. I would do it 13 times. Okay, and so what would the output do? Stop the YouTube, run it like I did, and you'll see that the answer is 64. Okay, and of course if I did f of 127, comma 22, if I inputted for x 127 and inputted for y 22, it would be 149. Great. Okay. Good. Question. Like I said before, this is basically the same as, from here below, is basically the same as before. What is the purpose of this line? Okay? Doesn't make sense. I mean, so I'd like to take out the line and show you what happens. You ready? Let's finish this first. I'm sorry, I should have finished this before. If you entered x and you entered y, what will be the output? The answer is x plus y. Okay, great. So we did this. But now, let's say I did the same program. Each time I entered 7 here. So this line that I erased said if y is not equal to 0, so 7 is not 0, so then we went further. Y was 13, we went further. Y was 22, we went further. So this line seems to be doing nothing whatsoever. Great. Let's try doing this program, but without that line, but with an input of 0 for y is equal to 0. So let's say I do 33 and the input is 0. Now I don't have this line. Let's see what would happen. So the computer stops, asks the user for a number, the user enters 33. The computer stops, asks the user for numbers for y, the user enters 0. Good. X is equal to x plus 1, this becomes 34. Y is equal to y minus 1, this becomes negative 1. If y is more than 0, is negative 1 more than 0? No, it's not. Negative 1 is less than 0, so it doesn't do this. And so it prints out x. What's x? 34. So if I didn't have this line, I would have this. F of 34 comma 0 is equal to, 33 comma 0 is equal to 34. Now that is not x plus 0. X plus 0 is the same thing. So Buzz, this is not right. 33 plus 0 is not 34. Okay? That was the purpose of that extra line. Let's just go through that extra line. Let's write in that extra line. It said, if y equals 0, go to b. Okay? So, now let's do it. The user enters 33 for x and 0 for y. If y is equal to 0, go to b, skips this whole thing, prints out on a piece of paper 33. And so, in the program that I wrote with this extra line, it's f of 33 comma 0 equals 33, which is exactly what we wanted. We wanted to make a program that does addition. Okay, so this is why that extra line was needed, just to make sure that it's done. Okay, great. Okay, let's do program number 6. I got to tell you, that's program number 6. So I did this to show you what the purpose was. Okay, now without this extra line, let's see. So we know what happens. Without this extra line, this does addition just like before. So we're doing now program number 6. Okay, and it does addition almost always. So this is program 6 without this extra line. So what does this program do? So it's an program that takes 2 inputs, and it does one of 2 things. Most of the time, it outputs x plus y. It outputs the addition. Why? Because it goes through this loop y times, each time incrementing x. So you're incrementing x once, twice, 3 times, y times. Very good. Okay? So this is if y is more than 0. But what happens if y is equal to 0? What's going to happen here? And I'm not even talking about negative numbers. Don't even think about it, negative numbers. What happens here? If the user enters x and then 0, what happens? Well, let's go through it. X is equal to x plus 1. Y is equal to y minus 1. That's going to go to 0. If y is 0, it's not going to do that. It's going to print out. So what's it going to print out? It's going to print out x plus 1. Now, could be that's what I wanted. Could be not. Whatever. But the point is, this input, this function, does one of 2 things. If I put in the other line, it's going to get rid of that, and it's just going to do this thing, x plus y. But if I don't have that extra line, it's going to put in like that. Okay, so this is program number 6. Okay, again, this is the reason why you have to be very, very careful with programming, because one little change messes things up. Great. Let's put in a new program. Stop. I'll write up the program. Okay, this is problem number 6. Let's go on. This gets a little bit more complicated. As we go on, we're going to get more and more complicated programs, but nothing too hard. Okay, so let's go through it. X is equal to question mark, y is equal to question mark, x is equal to x plus 1. You have 3 of these. Y is equal to y minus 1. There's a little a over here. Makes this a loop. Okay, if y is greater than 0, go to a. X is equal to x plus 1, x is equal to x 1, print x stop. Okay, so let's try something. Okay, let's say x, the user enters 17, and let's say y, the user enters 5. Okay, so let's see what's going to happen here. So, x is equal to x plus 1, 17 goes to 18, 19, 20, okay, they add 3, then y is equal to y minus 1. So this becomes from 5 to 4. Do it again. So this is going to go to 23, and this is going to go to 3. Because again, I just did this a little bit quickly. You're adding 3. Instead of adding 1, 2, 3, you just say add plus 3. Okay? And you do this again. So 3 is more than 0, so we go on. So this becomes 26, and this becomes 2. Still more than 0. 29, 1. Okay, still more than 0, so this becomes 32, and this becomes 0. Great. So, 32. Well, one second, we're not finished yet. We're not just printing out the number anymore. Now we're adding 1 and 2, so this becomes 34. Then you print out x, so it's going to be 34, and you get 0. So here's the function. If I put in 17 and 5, I get out 34. Good. Let's do another one. Okay, let's do another one. Let's do another input so we can see how this program works. Okay, if I put in 51 and I put in 3, what do I get? Let's see what happens. So you're going to add 3, you're going to get 54. This is going to go down to 2. You're going to add 3, you're going to get 57. This goes down to 1. You're going to add 3, you get 60. This goes down to 0. Is 0 greater than 0? No. So we go on to this, and we do plus 1, so this becomes 61, then it becomes 62. Okay, so let's see what happens. So this is f, okay, of 62, comma 3 is equal to, whoops, f of 51 times 3, comma 3 is equal to 62. Okay, let's do another one. F of 127, comma 10 is going to be, you should stop the tape and work it out yourself, okay, but basically it'll be 159. Okay? Okay, in general, how does this work? Okay, what does this function do? So in general, this is what we're looking at. F of x comma y, what's going to be the output? We have two inputs, we're going to call that x and y. What's going to be the output? And the answer is, for every y, we're going to add 3. So what we do is we start off with x, okay? And then for every single y, we do this loop. So it's going to be, and in that loop we add 3. So it's going to be add 3 times y. Okay? Let's just understand what this means. You add 3, 1, 2, 3, for every single y. Okay? But when you're finished, you're not really finished. You don't print it out. Then you add 2 more. So you add 2 more. Okay? And if you plug this in, 51 plus 3 times 3. 3 times 3 is 51 is 60, plus 2 is 62. Okay? Same thing here. 127 plus 3 times 10 is 157, plus 2 is 159. Okay, so that takes care of that. Great. Let's do number 7. I'm sorry, that was number 7. Sorry, that was number 7. Sorry. So that was number 7. Let's do number 8. Okay? So I'm going to erase. Let's do it. X is equal to question mark, so this is number 8. X is equal to question mark. Y is equal to 7. Z is equal to, label A says Z is equal to 5. Label B says X is equal to X plus 1. Z is equal to Z minus 1. If Z is greater than 0, go to B. Y is equal to Y minus 1. If Y is greater than 0, go to A, print X, stop. Great. Let's see what happens here. It says over here, nested loop, and I'll explain to you what that is in a second. But let's see what happens here. Here we have three variables, X, Y, and Z. Okay. X, we ask the user to fill in the X. So let's say the user fills in 17. It's my favorite number. No idea. Okay. Y is equal to 7. Z is equal to 5. Now let's see what happens. X is equal to X plus 1. Z is equal to Z minus 1. If Z is greater than 0, go to B. So here's a little loop. Let's see what this does. 17 goes to 18. Z goes to from 5 to 4. Okay. We're going to do that over and over again. So this is going to go. To 19, 20, 21, 20. This is going to go till 19. This is going to go to 3. This is going to go to 20. This is going to go to 2. This is going to go to 21. This is going to go to 1. It's going to go to 22. This is going to go to 0. Okay? So 17 plus 5 is 22. So that makes sense. Okay? But hold on, you're not finished. You're not finished. Because when Z, now Z is 0, so it's going to fall out of this loop. That's the phrase we use. Fall out of this loop. And it's going to go Y is equal to Y minus 1. So this is going to go down to 6. Okay? And then if Y is greater than 0, go to A. It's going to go all the way back up here. 6 is greater than 0, so it's going to go back to there. And look what it does. It resets this to 5. Okay? And it's going to do this again. Now this is what's called a nested loop, a loop within a loop. Let's just do one more example, well, one more of these, and we'll figure this out. So what's going to happen now? 22, 5, this is going to go to 23. Again, this is going to go to 4. But basically, at the end, this is going to go to 27. This is going to go to 0. Great. We're going to do this again. Okay? Okay? So, we go over here. Y is equal to Y minus 1. This goes to 5. We're going to do this loop again. Okay? So what happens? We reset Z to 5, and then we do this again. 27 plus 5 is 32. Okay? And we're going to decrement that. Still, we have to do it again. So we're going to do it again. This is going to go down to, this is going to go to 37. This is going to go to 3. This is going to go to plus 5 is 43. This is going to go to 2. This is going to go to plus 5 is 48. This is going to go to 1. Plus 5 is 53. This is going to go to 0. Okay. Finally, it's going to be 0. It says print X. What's going to be printed? 53. Okay, so let's just go through this. If I input 17, and by the way, that's the only thing that's input. Y is fixed. We don't input it. It's part of the program. Z is fixed. We don't input it. It's part of the program. It changes all the time. It's a variable, but we don't input it. So we write as follows. F of 17 is 53. Sounds good? Great. Let's do another one. Okay. These are warm-up exercises to see how this program works. Let's say the user enters 71. Okay. Then Y is equal to 7, Z is equal to 5. Okay. Let's see what happens again. So, Z is equal to 5. We're going to do this inner loop again and again. Okay. So, let's do it. I'm going to basically add 5 here. I'm going to get 76. Okay. I'm not changing this anymore because I know this little loop just goes from 5, adds 5. Okay, so you can change it if you want. In the beginning, you can change it. Let's do this again. 76, this goes down to 6. 76 plus 6 is 81. This goes down to 5. 81 plus 5 is 86. This goes down to 4. 91. This goes down to 3. 96. This goes down to 2. 101. This goes down to 1. 106. This goes down to 0. Okay? Okay? So, if I plug in 71, I'm going to get out 106. Okay? Okay, great. Let me just do it. If I plugged in 111, the output, stop the YouTube, figure it out yourself. You should see that you get out 146. Okay? How does this work? What does it do? Well, it does as follows. F of x is equal to x. You start off with x and you keep on adding. What do you add? Well, you're going to add 5. You're going to add 5. How many times will you add 5? Okay? And the answer is you will add 5 7 times. Okay? Another way of writing this is x plus 35. Okay? So this goes on. So you're adding x plus 35. Okay? Now let's just go through this. What's a nested loop? You have nested loops all the time. For example, you go to an ATM machine in a bank, okay? It asks you to enter your password. Okay? You put in your thing, it asks you to enter your password. Okay? Then you enter your password, and then it asks you what would you like to do. Okay? So it gives you a menu of things to do. You do the things. Okay? Now, you do one of the things. You finish, it asks you again, what would you like to do? What would you like to do? What would you like to do? Now, when you walk away, so that's a loop, asking you all the time what to do and then actually doing them, that's the inner loop. But then when you walk away, another person comes in, puts in their card, gives the computer asks it for a password, it does that. So that's the outer loop. Okay, the outer loop is doing something over and over and over, and then within that outer loop, you do it again. Same thing with playing a video game, right? Let's say you have 5 lives in the video game, so you have this. So it's counting down. Okay, you have 4 lives left, you have 3 lives left, you have 2 lives left, you have 1 life. That's the inner loop. But then, when you finish playing, what does it say? Would you like to play again? That's the outer loop, doing it over and over. So you have an inner loop and an outer loop. Okay, and that's called nested loops. Now we're going to play with these nested loops over and over here, and we're going to do more interesting things. Okay, so let's move on to number 9. Okay, and 9, we change y is equal to 7 to y is equal to question mark. Okay, and I think it's exactly this. Other than that, it's exactly the same. It's almost exactly the same. So let's work this out. Here, we don't just, okay, so this is now number 9. Okay. And beforehand, we did the inner loop, we did the outer loop a fixed amount of times, 7 times. Here, we're asking the user, how many times should we do this outer loop? Okay, and so we're going to let's plug in some numbers. So if I plug in 10, okay, this stops and asks the user for 2 numbers, not 1 number. So if if the user writes here 6, okay, instead of 7, let's do a little bit different number. Let's do 4, and then z is equal to 5. That's kind of fixed. Okay, great. So let's work this out. X is equal to x plus 1, z is equal to z minus 1. Go ahead, go do this over and over. So this inner loop is going to do it 5 times. So let's do it. So this becomes 10 goes to 10 plus 5 is 15. Okay? And then when you finish, you decrement y, so you get 3. Then this goes to 20, decrement y to 2. This goes to 25, decrement y to 1. This goes to 30, decrement y to 0. Okay? Now, y is equal to 0, and so you print out x, and so you get out 30. So let's write this up as a function. F of 10 comma 4, okay, is equal to what's going to be printed out at the end? 30. Okay, let's do another one. F of 19 comma 7. No, we did 7 because 7 we did already, because we had fixed 7. 9, okay, is going to equal to, stop the YouTube, figure it out, okay, and the answer is 9 times 5 is 45, plus 19 is 65, 64. Okay, and if you plug in f of 117, comma 12, okay, stop the YouTube, figure it out yourself, but the answer is 117 times plus 12 times 5 is 60. 12 times 5 is 60, so it's 177. Okay, so let's figure out a regular formula for this. This is f of x comma y. Now we have two inputs that we're doing here, okay, and it's equal to x. That's what you started off with, but then you add not 5 times 7 like you had before, but 5 times y. Okay, 5 times y. 5 times y is what you're doing. You're doing this inner loop. Every time you do this inner loop, you do it 5 times. You're adding 5. How many times do you do this inner loop? Answer, y times. Key point. Here, the input is 2 inputs because you're asking the user for 2 numbers, and the function is in terms of those 2 numbers. Okay, so it makes sense. Great. Let's do number 10. Okay, number 10 is wrong, but it's similar. Okay, so let's do number 10. Okay. Now, let's just do this. Number 8, we had an inner loop, okay, but we had y to fix as 7 and z fixed as 5. Then number 9, we had an inner loop, but we asked the question, how many times should we do the outer loop? Now we're doing the same thing. We're asking the question, how many times should we do the inner loop? My goal is as follows. Don't write this. My goal is x comma y comma z should equal to x plus y times z. Okay? In other words, start off with something, do the inner loop, z times. How many times should you do the inner loop? Y times z times. Okay? Okay, that's my goal. It's not going to work because I made a mistake here. But let's see how this works. Okay? I just changed from z is equal to 5 to z is equal to question mark. So, let's just go through this. Let's say let's pick small numbers, 10, and we'll pick 3 here, and we'll pick 5 here. No, we don't want to pick 5 because we just picked 5. Let's do 4, okay? And so let's do this. So we stop, we ask the user for 3 numbers, we put the 3 numbers in, then x is equal to x plus 1, so this becomes 11. Z is equal to z minus 1, this becomes 3. Z is more than 0, yes it is, so we do this again, 12. This becomes 2, this becomes 13, this becomes 1, this becomes 14, this becomes 0. Okay, so basically we added 4. Then, watch what happens next. Y is equal to y minus 1. 3, then 2. That becomes a 2. Okay, and then y is equal to go to a. Boom, we go all the way up again, and we ask the user for another number. I don't want to do that another number. I want to do the whole thing a fixed amount of times. So this is not the right thing. We're not going to ask the user again for another number. Okay, that's not what I want to do. So we have to change this program. So that's why it says on the bottom here, this is wrong. We're asking the user again for another number. Okay, number 11 is right. So let me show you how number 11 works. So this is number 11. Okay, and it works as follows. X is equal to question mark. Y is equal to question mark. Z is equal to question mark. Get 3 pieces of information. X is what you start with. Y is how many times do the outer loop. Z is how many times do the inner loop. Okay, great. Then you do as follows. A, W is equal to Z. Okay, and then you don't change Z, you change W. W is equal to W minus 1, and then if W is more than 0. Okay, now you work through this. Let's say this starts at 10, Y starts at, what did I just have? This was 4, I think, this was 3. Let's see what happens here. Okay, let's actually do it. There's another variable here called W, and so we're going to do this. Ready? X is equal to 0, question mark, it puts in 10. Y is equal to question mark, the user puts in 3. Z is equal to 4, Z is equal to question mark, the user puts in 4. And then look what it says, W is equal to Z, so this becomes 4. So let's see what happens. X is equal to X plus 1, this becomes 11. W is equal to W minus 1, this becomes a 3. Okay, and then we do it again, because W is more than 1. So this becomes 12, this becomes 2, this becomes 13, this becomes 1, this becomes 14, this becomes 0. If y is greater than 0, so y is equal to y minus 1, this becomes 2. Y is greater than 0, we go back here to A and we reset the inner counter. Instead of asking the user for an inner counter, we reset it to what it was set before. Z is equal to 4. So we have to keep that in memory, but we do this again. Okay, let's do this quickly. We're going to go down W 4 times. We're going to go up. This is going to go to 18. This is going to go 5, 4, 3, 2, 1, 0. This is going to go down to 1. Okay, we never change this. There's no Z equals anything over here. We never change this. We just need this to keep track of how many times to do the inner thing. Okay, let's do this again. This becomes 22. 18 plus 4 is 22. This goes all the way down, etc., etc. This becomes 26. This becomes 0. Okay, and so let's see what happens. We are now, y is equal to 0, so we go full out and we say f of 10, comma, 3, comma, 4. Okay. 3, comma, 4. I think I did this too many times. 14, so this becomes 2. So it's going to be 18 and 2. 22. sorry, no, let's do this again. Okay, we started off, this is 3, so this turn, okay, when we finish this, this is going to be 14, this is going to be 2. Okay, good. So, 14, 2. Great, sorry. Okay, made a mistake. So this becomes, we'll do this again, this becomes 18, this becomes 1, this becomes 22, this becomes 0. Okay, so the output is 22. Okay, sorry about that. So I did it too quickly. Okay, if I put in 117, okay, and I put in 7 here and 10 here, okay, stop the computer, stop the WhatsApp, stop the YouTube, and work this out. You'll see the answer you get is 187. Okay, if I put in f of 51, comma 9, comma 3. Okay, stop the YouTube, figure it out. You should get 78. 9 times 3 is 27, plus 1, 78. 28. Okay? Okay, in general, you get as follows. F of x times y times z. What's the function? Notice there are 3 inputs. W is not an input. We don't put that in as inputs. If you plug in 3 inputs, you're going to get out x plus y times z. Okay? You can put parentheses around that, but that's not necessary. Okay, great. Okay? Now, I want you to try to do number 12 by yourself. It's called collapsing a loop. It basically says, instead of doing this whole thing, okay, sorry, I should do this with different chalk. Instead of doing that whole thing, okay, change that whole thing to the loop. Instead of doing this whole thing, so cross it out and do x equals x plus z. You added that thing. It basically does the same thing because this is exactly what's done here. X is equal to x plus z. Just add that. And I think we also get rid of that. We don't need this either. Okay, so that's number 12. You should work it out. I promise you, on the second, on the final, I will give you a program, and I will ask you to plug in different numbers. I'll give you the numbers to plug in, and then I will ask you what function does this program do. So you're going to have to get used to this. You're going to have to do a lot of programs, okay, to get used to it. Let's go. Let's move on. Okay, great. So that's number 12. We're going to do the next 5. 6 programs. We're going to do the next 6 programs, or most of them, and these get more interesting. Okay, so far all we've been doing is taking an input number and adding to it, but we're going to do some more interesting stuff as we go on. And we get more interesting programs, and you have to figure out what they do. Okay, so number 13, it says sometimes you stop and sometimes you don't. Okay, and it's basically as follows. It's a simple program. This is 13. Okay. X is equal to question mark. Y is equal to question mark. A. If y is greater than x, go to A. Where's A? That's right, A. Okay. Print x. Stop. Okay, so let's plug this in. So let's say x and y, you stop, and the user enters 7 over here and enters a 19 over here. Let's see what will happen. Okay, if y is greater than x, then go to A. It's going to go here. Okay. Now, let's do what's going to happen now. If y is greater than x, go to a. If y is greater than x, go to a. If y is greater than x, go to a. It's just going to do this over and over and over again. Okay? So, let's see what happens. F of x comma, f of 7 comma 19 is never going to stop. It's never going to print out anything. And so we write that as up arrow. Okay? As opposed to that, if I do 10 comma 3, let's see what happens here. 10 comma 3, I'm going to plug in here 10 and 3. Here's 10, here's 3. What happens here? If y is greater than x, no, it's not. Okay, so it's going to print out x. It's going to print out 10. Okay? And all depends on if one number is bigger than the other. So if I plug in f of 20 comma 20, 20 comma 20 is not bigger than 20 is not bigger than 20, so it's not going to do this loop. It's going to put out 20. If I plug in f of 20 comma 21, it goes to an infinite loop. Okay? So, question, what does this program do? And the answer is f of x comma y does one of two things. It either prints out x. When does it do this? When if y is less than or equal to x, otherwise it goes into an infinite loop. So we write this as else. It goes into an infinite loop. So it either prints out x or it goes into an infinite loop. Great. Next, let's do number 14. Number 14. Okay. X equals question mark. A. Let's label A. If x equals 0, go to E. X equals x minus 5, go to A. E. Print x, stop. Okay, let's see what happens. Okay. Let's say the user enters the number 20. Oops. The user enters the number 2020. Okay, so let's go through this. If x is equal to 0, no, it's not equal to 0. X is equal to x minus 5. So this becomes 15. Go to A. This is called an before we had a conditional branch, okay, you branch, you jump back up if a condition is met. This is called an unconditional branch. Means don't ask any questions, just jump. So this is like this, okay, and we do it again. This is if x is equal to 0, no it's not, so we do x is equal to x minus 5, so it goes to 10. Go back, it's not equal to 0, so it goes to 5. Go back, it's not equal to 0, so it goes to 0. 5 minus 5 is 0. Go back. If x is equal to 0, yes, it is equal to 0, so go to E. If you want, you can think of E as exit. Get out of this program. That's why I labeled it E instead of B. Okay, so it outputs 0. Okay, stops. Okay, so that takes care of that. So let's write this in. If I plug in 20, I get out 0. Very good. Question, what happens if I plug in 19? Okay. Work it out by yourself and see what you get. Okay, basically, it's going to subtract 5 from 19, so let's do it. You're going to get 14, you're going to start off with 19, you go down to 14, you go down to 9, 14 minus 5 is 9. You're going to go to 4. You're going to go to negative 1. You're going to go to negative 6. You're going to go to negative 11. You're going to go to negative 16. Keep on going forever and ever. Will it ever stop? No, it won't. So it's going to go up like that. Okay? Okay? Let's say I did f of 35. Well, you work it out. You'll see it outputs 0. F of 37, it's never going to stop. Okay? Plug in a few values and see what happens. Basically, it's going to stop if it'll ever reach, if you keep on subtracting 5, if it'll ever reach 0. Okay? So we have the following function. F of x is equal to one of two things. Either it's going to output a 0 or it's going to go into an infinite loop. When does it output a 0? If x is divisible by 5. Else it does that. Okay. So it's a cute little problem, and it does that. Sounds good? Okay, 3 more problems. Okay, this is problem 15. X is equal to question mark. X is equal to x plus 1. If x is greater than 10, go to A, stop. So let's say that the user enters 20 in the thing. So let's see what happens. So then this becomes 21, and if 20 is greater than 10, it is, go to A, so then it goes to 22, and then it goes to 23, and then it goes to 24, etc. Okay, and it will go on forever and ever. So we have if f of 20, if the guy enters 20, then it goes up arrow. Okay, great. Okay, great. What happens if he enters 5? So let's see what happens. 5 is equal to 5 plus 1, 6. If x is greater than 10, 6 is not greater than 10, it stops. So we write stops. It doesn't print anything, but it stops. So stops is the opposite of going into an infinite loop. It's grounded, stops, so we do it a down arrow. Okay, great. Let's see what happens if he enters 10. So 10, the guy enters 10. 10 is equal, 10 plus 1 is 11, so this becomes 11. If 11 is more than 10, yes it is, it goes on to 12, goes on to 13, goes on to 14, etc., etc. Okay, so if 10 is entered, then what happens? It goes into an infinite loop. Okay? Okay, great. What happens if he enters 9? So then this becomes 10. Is 10 greater than 10? No, it doesn't, so it stops. So that's the cutoff point. If he enters 9, it stops. Okay? So question, what does this function do? And we can write it out like this. F of x is equal, it does one of two things. It either goes up or goes down. Okay? It either goes into an infinite loop or it stops. Okay? It goes into an infinite loop if x is less than or equal to 9. Okay? Otherwise, it goes into an infinite loop. If it's not less than or equal to 9. If it's 10 or more, it goes into an infinite loop. So that's the way we write it. One of two things. Great. That was that. Let's do this one. We'll do it fairly quickly. Let's plug in a number. Okay. Let's just read it. X is equal to question mark. Ask the user for a number. If x is less than 13, go to A. If x is less than 13, go to A. If x is less than 13, go to A. We've seen this before. That's an infinite loop. If x is less than 34, go to B. Otherwise, do this. So let's go through this. Okay. Let's plug in a number. If you plug in 5, then 5 is less than 13. It's going to do this over and over and over. It goes into an infinite loop. Okay. If you plug in 15, let's see what happens if you plug in 15. Okay. If 15 is less than 13, no, it's not. So it goes here. If x is less than 34, yes, 15 is less than 34. So it's going to go to B and just going to print out 15. That sounds good. It just prints goes to B. B is never changed, prints out. Okay, otherwise, let's say you plug in 75. What happens then? So, is 75 less than 13? No. Is 75 less than 34? No. So it's going to do x is equal to x plus 5, so this becomes 80, and then it prints and stops. It goes like that. Okay, so this program, the reason why I brought this program is it doesn't do one of two things, it does one of three things. Okay, and we can write it as follows. F of x does one of three things. Either it goes to an infinite loop, okay, or it prints x, or it prints x plus 5. Okay, it goes to an infinite loop if x is less than 13. That's exactly what it says here. Otherwise, if x, let's write it like this, x is less than or equal to 14 or 34, it prints x, goes to b and prints x. Okay, if x is more than, you could write else, but if x is more than or equal to 35, it prints x plus 5. Okay, so that's what these two programs do. It's a good idea to put in some more examples. Great, so that takes care of that, and that takes care of program number 15 and 16. Okay, let me just tell you what program 17 does. Okay, I don't want to go through it, but you can see it. The point about 17 is it prints more than one value. It prints several values. You have to follow the program and see. Sometimes it prints a few things, sometimes it prints forever and ever. I don't remember exactly. Okay, so it just prints more than one thing. So far, we've always had output is one number, but here it can have more than one number. Okay, and finally, let's do number 18. Okay, okay. So I'm not going to rewrite number 18. You have it on the paper. But I would like you to plug in the number 13 and see what you get out. Okay? Stop the YouTube, sit down with a piece of paper and a pen, write down the number 13 and follow the program. Start the YouTube again. Okay. If you spent 20 minutes, I ask you the following question. Did it halt or not? Okay? And the answer is, I have no idea. Okay? I have no idea if it will halt or not. Okay, because I've tried it for 20 minutes and I can't tell whether or not it halts. It's a wild, crazy, different program. Okay? Great. Now let me ask you the following question. Can you get a program to look at program number 18 and tell if it will halt or not? And this is the beginning of what we called the halting problem. And the answer is no such program exists. Absolutely no such program exists. We're going to prove that fact, or we're going to attempt to prove that fact in a few minutes, but now we can understand what the problem is. Here you have a complicated program, and it's hard to tell whether it stops or not. Now, let me just go through this. We did 17 programs before. We were able to tell whether or not those programs halted or not, or didn't halt. Okay? But the 18th was a little bit harder. Okay? Now, I can tell you like this. I teach 3 types of programming classes. Elementary program, intermediate programming, and advanced programming. The elementary programs are all first-year students, and their programs are at most 15 lines. And I can look at those programs, and I can tell whether those programs whether they will halt or they don't halt. Okay? I can just look at the programs and see that. Will they halt or will they not halt? In contrast, the intermediate programming classes, those programs get to be 2 or 3 pages long, and there I have a harder time telling whether the programs will halt or not for all inputs. So I have to run them a few times and get a feel for that. The advanced programming classes, some of those classes, the program gets to be tens of pages. There's no way in the world that I can possibly do that. So even for myself, small programs I can tell. Larger programs are much harder. Okay? Same thing. you might be able to write a program to tell whether another small program will halt. Okay? But if you don't, I mean, if the programs are large, then you won't be able to do it. Okay? So, and there's a rumor or a legend that Microsoft Windows is made out of something like 40 million lines of code. There's no way in the world that people can do it. Not only one person can't do it, but in Microsoft they have something like 35,000 people working there. And they can't figure out when certain things go into an infinite loop. That's why you have an infinite loop. Okay, now let's just go through, before we do this, before we prove that the halting problem can't be solved, let's just go through some interesting facts about the halting problem. Okay, the first idea is as follows. This question of can a program solve the halting problem, came up with Alan Turing. And Turing did this in the 1930s, before there were any computers. So before there were any computers, Alan Turing figured out what a computer cannot do. That's an amazing thing. Okay? So before the engineers figured out what computers can do, Alan Turing and several other mathematicians figured out what a computer cannot do, even before they existed. So if you watch The Imitation Game, there you have Alan Turing saving the world from Nazis breaking their code, but you have to realize that even before that, 10 years earlier, 5 years earlier, he was already solving what computers cannot do. So that's a very interesting thing, the power of theory rather than applications. Okay, another thing I wanted to say is computers are amazing things. We learn all the amazing things that they can do, but there are certain limitations, and that's what we're going to talk about now. Okay, just some more lingo. We say that if a computer can solve a problem, the problem is decidable. In other words, the computer can decide, as in decision problem, will it halt or will not. As opposed to that, if a computer cannot do it, it's undecidable. You cannot figure out whether it will do it or not. Okay? Okay. Another thing. So basically what we're saying is the halting problem is undecidable. Okay, we're going to prove this. Turing proved this. We're going to give an intuition of the proof in a few minutes. But I want to do something else. What happens when a computer goes for a long period of time? You see the computer saying on top, it's saying not responding. What's that all about? Well, your computer is made out of different parts. One of the parts is called an operating system. The operating system controls the other programs. So what happens sometimes is the operating system is written by Microsoft or written by Windows, whatever. They're very smart. Sometimes a program's running and the computer thinks, I think this could be in an infinite loop. Now, he's not sure that it's in an infinite loop. The operating system is not sure that the program's in an infinite loop because of the halting problem. It can't tell. Because computer programs sometimes can run for 20 minutes straight before it comes out with an answer, or 25 minutes, or 30 minutes. So you can't always tell when something's in an infinite loop. So the computer won't know for sure. So what the operating system does is it says not responding. In other words, it thinks there's a problem, but he's not sure. Sometimes the computer will just say, you know what, I think there's probably a problem, and it will stop it. Sometimes it'll fall out of the infinite loop by itself, and sometimes the user has to press Control-Alt-Delete and break out of it. Okay? You get that a lot with the internet. Okay? Viruses basically go into your computer and they don't stop. Okay? So that's what you're doing. So again, what's going on is that the operating system cannot solve the halting problem, and so it tries to solve it and tries to take a guess at it, and that's what not responding is all about. Okay. Now, you might say, hey, I have a simple way of solving the halting problem. Run the program for 20 minutes and see if it halts. Okay? But the answer is it won't necessarily hold, because there are many programs that we know that need more than 20 minutes. They need 25 minutes. They need 30 minutes. There are programs you can write that need 200 hours, not 201 hours.
I'm hungry.
Okay. So we're going to have to deal with that. Okay? Come, let's say hello to the class. This is Princess Miriam. Say good morning. Okay, now go upstairs and I'll give you food. Okay, so that's that. Great. Now, what I want to do is I want to talk about a proof of it. Okay, I want to talk about proof. So I want to give a few different proofs, but not the real technical proof, but let's just give you an intuition. Okay, there's a man named Bill Gates. Bill Gates owns Microsoft, or he did own Microsoft, whatever. He has the most stocks in Microsoft. Bill Gates would love to have a program that can solve the halting problem. Okay, because every time a program goes into an infinite loop and he didn't see it, and the program doesn't catch it, he looks like a fool. He would like to write programs that never go into an infinite loop. Okay, the fact that Bill Gates doesn't have a halting problem decider means there's something wrong. Now you have to understand, he has 35,000 of the most intelligent people working in Microsoft, and they can't write it. They can't write a program that will test for the halting problem. So again, what Bill Gates wants is some big program, and every program that comes out of Microsoft should go through this big program. This big program should test, will this ever go into an infinite loop? If it does, it should tell, yes, this will go into an infinite loop. It goes back to the engineers have to fix the problem. When they fix the problem, it goes through again this big program and sees, will it ever go into an infinite loop? Again and again and again, until all the infinite loops are gone. Okay? Then Bill Gates is going to be giving out a perfect program that never goes into an infinite loop. Okay? Such a thing doesn't exist. Okay? And a sociological proof is, if you have 35,000 of the most intelligent people in America working for you and you still can't write it, you get the impression it can't be written. Okay? So that's not really a proof, that's just an intuition. Okay? The proof is much more interesting. The proof is, and we're not going through the proof, you're not responsible for the proof, but it is in the book and it's very, very readable. And the proof is as follows, especially if you can read these programs, the proof is as follows. Self-reference. Okay? What do we have? We want a computer program that can deal with computer programs. Okay? We want a computer program that can deal with computer programs. We want a computer program that can tell if a computer program will halt or not halt. Now that's a very deep thing. We want a computer program to tell if a computer program will halt. So you have computers talking about themselves. Whenever you have something talking about themselves, and we've had a lot of that, we've had English sentences talking about themselves, we'd have sets talking about themselves, we talked about math talking about themselves, in time travel paradoxes we talked about events talking about themselves. Whenever you have something like that, something evaluating itself, the Barber paradox, villagers cutting villagers' hair, we have some limitations. The limitation that we have is that the halting problem is not solvable. Okay? So the halting problem is not solvable. Okay. Okay, again, we are going to skip the details. It's in section 6.2, but it is important. Okay, great. More. Okay, let me just restate what the halting problem is in English. Okay, and then we're going to talk about other problems also that are unsolvable. The halting problem. So let's restate the halting problem. The halting problem says as follows. Question: can you write a program that will accept a program and an input to that program and tell whether or not that program with that input will halt. Okay? So for example, can you write a program that will accept program number 18 and input 13 to that and tell, will it halt or will it not? Halt. Okay? Will it halt or will it go into an infinite loop? Okay? And the answer is, that's undecidable. Okay? Okay, so again, let me just restate. Can you write a program? Can you write an algorithm? Does there exist a machine? Does there exist a computer that can accept a program and a number that goes into the program and tell whether or not that program will halt or go into an infinite loop? And the answer is no. No such program exists. Okay? Okay. Now, that's one example of an undecidable problem. We're going to have 3 more examples of an undecidable problem, and we have to do that. Okay? These examples are on your chart, on your paper, so let's do that. Okay? One is called the zero program problem. I'm sorry, we're going to have 1, 2, 3. 1, 2, 3. Yeah, problem. Zero program problem. Okay, and I listed off here, let's just say it. Give it a program, tell if it will always print 0 regardless of what input is entered. Okay, so let's go through. There's 4 programs here. I'd like to go through this. Look at the first program. X is equal to 0, question mark, print 0, stop. Okay, now that program, if you input 15, it will print 0. If you input 5017, it will print 0. If you input any number, it will print 0. That's very good. Okay, let's look at the next one. X is equal to question mark, X is equal to X, I'm sorry, let's do this. Y is equal to X plus 2, Y is equal to Y minus 1, Y is equal to Y minus 1. Okay, print Y minus X. Let's just follow that program. Let's say the guy enters, here's X, here's Y, the guy enters 17 here, then Y is equal to X plus 2, so this becomes 19, Y is equal to Y minus 1, so this becomes 18, Y is equal to Y minus 1, this becomes 17, print Y minus X, 17 minus 17, it's going to be 0. It's going to print 0. Now, I could plug in 175, I can plug in any number. All it does is add 2 here, and then subtract 2, 1, 2, and then print out the subtraction of those 2. It's going to print out 0. It's a stupid, complicated program that always prints out 0. Great. Let's look at the third one. Okay, X is equal to question mark, Y is equal to 14. Print X minus X, stop. Okay, what's X minus X? No matter what X is, what is X minus X? X minus X is 0. So that's not a very interesting program. So again, the third program will also give a yes answer. Okay, a yes answer means this is a 0 program. This, no matter what is input, will give you a 0. Okay, let's do the last one. The last one is a little bit more complicated. Okay, it's a fourth example of a 0 program. Well, let's go through it. X is equal to question mark, Y is equal to 10, Z is equal to X times Y, W is equal to 5, A. Z is equal to Z minus 2 times X, W is equal to W minus 1. If W is greater than 0, go to A, print Z, stop. Okay, so we have a little loop over here. It goes like this. Okay, and let's see, let's plug in, let's say, we have a lot of variables here, X, Y, Z, and W. Okay, let's say the user enters 51. Then Y is equal to 10. That's good. Z is equal to x times y. 51 times 10 is 510. W is equal to 5. Okay? Now look what's going to happen. Z is equal to z minus 2 times x. Z is equal to z minus 2 times x. So 510 minus 2 times 51, so is 400. 2 times 50 is 410, 408. Okay? Okay, good. W is equal to W minus 1. Okay, so this goes down to 4. And we're going to do this again. W is more than 1, so we do this again. So basically, this is going to equal to 2 times 50 is 308, minus 2 is 306. Okay. W is more than 1, so this becomes, so this becomes 3. W is more than 0, so it does it again. So this becomes 204, and this becomes 2. That's good. And we do it again. This becomes 102. This is 1. That's very good. And next, do this one more time. 102 minus 2 times 51. 2 times 50, this becomes 0. This becomes 0. Print Z. It's going to print out 0. Stop. It prints out 0. So we plug in f of 51. We get out 0. Okay? I claim this program, no matter what you put in, let's just plug it in. Take any number, put it in here. Y is equal to 10. Z is equal to x times y. So basically, Z is equal to x times the number that you, 10 times the number you put in. And then what you can do is this loop 5 times. Each one of these 5 times, you're subtracting 2 times x. So you're taking 10 times x, you're subtracting 2 times x, minus 2 times x, minus 2 times x, minus 2 times x, minus 2 times x. So let's do that again. 10x minus 2x minus 2x minus 2x minus 2x minus 2x is 0x. 0x is 0. So no matter what you plug in, you're going to get out 0. So this is a complicated, stupid program that always puts out the 0. Okay? Great. That's a very nice program. Okay, so now we have the 0 program problem. Let me tell you what the 0 program problem is. Given a number, given program 0, given a program, question, will it always print out 0? Okay. Now, here were 4 problems that we looked at, and we were able to tell, yes, they always give out 0. But I can make a much more complicated program, and it would be hard to figure out, will it always print out 0? Now, here's an attempted solution. Plug in 1. See what the output is. See if it's 0, you're finished. I'm sorry. If it's 0, you know that 1 is 0. Okay. Plug in 2. Plug in 3, plug in 4, plug in 5, plug in 6. Now, let's say you plug in 6 and you get an output of 17. Okay, then what do you know? This program will not always output 0. I plugged in 6 and I got out 17. Doesn't output 0. So then I can answer, no, this is not a 0 program. But what happens if it's 6 it plugs in 0, 7 it plugs in 0, 8 it plugs in 0, 9 it plugs in 0, 10,000 it plugs in 0, 10,001, 10,002, and I go to 10 billion. Can I safely say this program will print out 0? And the answer is no. Okay? Computers can deal with numbers, all numbers. I need some way to get all numbers. Okay? So the 0 program problem, which says, given a program, tell, will this program output a 0, yes or no? And the answer is, computers cannot deal with that problem. Computers cannot determine such a program. Great. Let's talk about the printing 42 problem. The printing 42 problem is very simple. I just want to know, is there some, given a program, is there some input I can put in there such that I can get out the number 42? I made up the number 42. I could have done it with any number, but I did it with number 42 because number 42 is the answer to life's great mysteries. Can I do it? Okay, and the answer is no. Okay, here's two programs. We want to tell, will these programs print out 42? Okay, so let's try it with this one. Let's say I plug in 42 here. Let's see what happens. If x is more than 56, 42 is not more than 56, so we go to the next line. Is x less than 35? No, it's not less than 35. 42 is not less than 35, we go to the next line. So what do we get? X is equal to x minus 5. 42 minus 5 is 37. It's going to print out 37. So f of 42 is equal to 37. Question, is there some number I can put in here that's going to give me not 37, but it's going to give me 42? Okay, the obvious thing is, look, I subtract 5 from it, so why don't we try in 47? If I put in 47, let's see what would happen. Is 47 more than 56? No, it's not. Is 47 less than 35? No, it's not. Okay, so 47 minus 5 is 42. Okay, so yes, this program will put out a 42. Okay, right here. The only number that it will do is if you plug in 47, you'll get out of 42. Okay, so the answer to this program is yes, this is. Now, we were able to see it, and you might be able to write a computer that can do for such a small program, but for any program whatsoever, to tell whether it will ever print out 42, that you can't do. Now, you might want to try the following. Plug in 1, see if 42 is being printed out. If yes, you stop and you say, yes, I can get out of 42. Otherwise, try 2, try 3, try 4. Okay, what happens if you go to 10 billion and you didn't get out of 42? That doesn't mean you don't plug in 10 billion and 2. Maybe it'll give you a 42. So it's very hard. Okay, let's do this one. X is equal to question mark. If x is less than 0, go to E. X is greater than 50. Add 54, print x. Okay, let's try something. Let's try plugging in 42. Will that give me 42? Let's see. 42, no. 42 plus, is 42 less than 0? No, it's not. So then what you do 42 plus 54 is 96. It's going to print out 96. That doesn't help you. Okay. Now, so let's try another number. Let's try f of 31. Okay. What's going to be printed out of 31? You're going to get 85. That doesn't help you. What do you want? You want 42 to get printed out. So how about this? F of minus 17. Why? Because minus 17 plus 54 is 54 minus 17 is 4 minus, no, that's not enough. Anyways, it doesn't matter because plugging in a negative number will just print out the negative number. It's not going to be able to do that. So there's no way you're going to do 54 minus 42 is 12. Is 12. So you might say, hey, plug in negative 12. Negative 12 plus 54 is 42. But that doesn't work. So let's do negative 12 is equal to negative 12 will equal to negative 12 because of this line. So the answer is no here. The answer was yes here. The answer is no here. Okay? You'll never find an integer that will be able to put out a 42. Great. Now let's go to the third one. The third one we need some background. So let's do some background. Okay? The background is something called the Goldbach conjecture. And let me just explain to you what it is. Take the number 4. This is equal to 2 plus 2. 2 is a prime. 2 is a prime. So this is a sum of 2 primes. Take the number 6. That's equal to 3 plus 3. That's a prime and that's a prime. Take the number 8. That's equal to 2 plus 6, it's equal to 3 plus 5. 3 is a prime and 5 is prime. Take the number 10. 10 is equal to 5 plus 5. 12. 12 is equal to 5 plus 7. 14. 14 is equal to 7 plus 7. 16. 16 is equal to 3 plus 13. Right? 3 is a prime, 13 is a prime. 18. 18 is equal to 5 plus 13. Prime, prime. 20. 20 is equal to 3 plus 17. 22. 22 is equal to 5 plus 17. 24 is equal to 23 plus 2. No. No, that's 25. 24 is equal to 21. No. That's embarrassing. 23. No. 20. No. 19. 19 plus 5. 5 plus 19. 26. Okay. 26 is 7 plus 19. Both prime numbers. Dot, 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 dot. Okay. Okay. So this is called question. Does this go on forever? Answer. About 300 years ago, there was a guy in Germany named Goldbach, and he worked out a couple of hundred even numbers, and he showed that every even number, I'm sorry, he did not show. He did not show. Goldbach conjecture. Okay, he said he worked out for the first couple of hundred numbers, and he showed every even number for the first couple of hundred numbers is a sum of two primes. Okay, and he made a conjecture. He said, you know what? I think this is true for all numbers. Okay, but he couldn't prove it. Then in the 50s and the 60s, we got computers, and we were able to go to billions and billions of numbers. Nowadays, we can go to trillions and trillions of numbers, and we can show that every even number in trillions and trillions of numbers is equal to the sum of two primes. Goldbach asked the following. Now we can ask the following question. You ready? Is it true for all numbers? Okay. Now, this program, number 4, what it does is it searches if x is even but not the sum of two primes, print 42. That's what this program does. It prints 42 if it can find a number x that's not 42. Okay, okay. So now we ask the following question: will this program ever print 42? Okay, it either prints 42 or it goes on forever and ever, or it just stops. Okay, one of two things. So let's write this. F of x, it either stops or prints 42. If Goldbach is wrong. Else. Well, it's a little bit simple, but it's not really what that program does. But don't really want to write that. But it's either going to stop or it's going to print out 42. It's going to stop if it's whatever. It's going to print out 42 if there's a counter example, if there's something that shows that this is wrong. Okay. Question: is the Goldbach conjecture true or false? In other words, will it never print out 42? Answer: I don't know. Neither does any mathematician in the world. Neither does anybody else. So this is an unanswerable question, and a computer can't answer the question either. Okay, so this is a third hard problem. Let's go through it. We had the halting problem, which is unanswerable, which is undecidable. We had the 0 program problem. We had the printing 42 problem. We have one more problem that we're going to talk about, and that's called the equivalent program problem. Let's talk about that. Okay. Okay. And this problem asks the following simple question. Given two programs, tell if they're exactly the same programs, then there's no problem. It's solved. It does the same thing. But question, this program, does it do the same thing? Okay? For example, I teach programming, so I tell the students, write a program that does this. So he writes one program, he writes another program. Do they do the same thing? Okay? So here's a simple way of solving it. Plug in 1 into this program, plug in 1 to this program, see if they both give out the same answer. If they both give out the same answer, yippee, go on to 2. Plug in 2 into this program, plug in 2 into this program, see if they give out the same answer. If yes, good. Try 3, try 4. Now, let's say you plug in the number 17 into this program, you get out 52. You plug in 17 into this program, you get out 53. Then you found an input that the output is not the same. Okay? So you can answer no, they're not equivalent programs. They don't do the same thing. Okay. Okay. But let's say you plug in 1, you get the same answer. You plug in 2, you get the same answer. You plug in 3, you get the same answer. You plug in 4, you get the same answer. Dot, 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 dot. You plug in 5 billion, you get the same answer. You plug in 5 billion and 1, you get the same answer. Do you then know that they're always the same? Answer, no you don't. Okay? You still have to try. We need to know this is true for every single program. Okay. So I'd like to go through, not really go through, but tell you how this works. Okay, so the equivalent program problem asks the following. Given two programs, do they perform the same function? So we spent a lot of time going from a program to a function, program to a function. Just tell if those two programs are the same. So in the handout, I give you 3 pairs of functions, of programs, program, pairs of programs, okay? And what you have to do is you have to go through each one of those pairs and see they're not the same program, but do they perform the same function, okay? So let me just give you the answers to these 3 things, okay? And then you can get it. Okay, but you have to do this on your own. I promise you, on the final, on the midterm, on the final, I will give you 2 programs, and I'll say, are they equivalent programs? Okay, and so if you look at the one on the left, it's a f of x equals 3 times x plus 5, and this one is also g of x equals, if you work out what it does, it multiplies the number by x plus 5. Okay? This one is f of x comma y comma z is equal to x plus y times z. The outer loop is y, the inner loop is z. Okay? And this one is g of x comma y comma z, and this does x plus, the outer loop is z and the inner loop is y. Okay? Now, but y times z is equal to z times y. So those are the same functions, really. Okay? These two are also the same functions. Okay? And the answer to both of these are f of x equals 3x plus 2. And this one is f of y equals 3y plus 2. They're different variables, but the output is the same. The functions are really the same. So all three of these, this is equivalent to this is equivalent to this is equivalent to this. They're different programs, but they do the same thing. Also, this program down here, it does 3 times x first and then adds 2. Here, it first adds 2 and then does 3 times x, or 3 times the input variable. So they're all the same. So these are examples of equivalent programs. Good. Now, you might say to yourself, look, we spent all our lives learning amazing things that computers can do, and you've shown me 4 problems that computers cannot do. Let's go through the 4 problems. They cannot solve the halting problem, cannot solve the 0 program problem, cannot solve the printing 42 problem, and it cannot solve the equivalent program problem. Again, all 4 of them are objective questions. They have yes/no answers, and yet no computer can figure them out. Okay? The way we prove that they can figure that out, by the way, this is all done in section 6.3. The way we prove it is we show that these other comparing problems, we're not responsible for this. I say it in the thing, you're not responsible for it, but it's not such a hard read. You basically show that all 3 of these other problems are even harder than the halting problem. If the halting problem can't be solved by a computer, so these other things, 0 program, 42, and the equivalence program, those problems are even harder than the halting problem. They for surely can't be done. Okay, great. Now, we spent our whole life dealing with what computers can do. So we say they're computable. Things that computers can do. Okay? As opposed to that, we could talk about all problems. Okay? And what we showed was computer problems, this is what you did your entire life. You talked about things that computer could do. But we showed that there are 4 things out here. 1, 2, 3, 4. This is the halting problem. This is the 0 program problem. This is the printing 42. Print 42. Equivalent program. These things are problems. They're easy to describe. They're objective problems, and yet they're not computable. No computer can do them. Okay, so they're out there. Now you might say, that's not very interesting. Okay, there's thousands and thousands and thousands of problems that computer can solve, and you found 4 that can't be solved. This is the beginning of I'm just giving you the tippy top of the iceberg. Okay, in fact, we could do the following. I say this in the book. You're not responsible for the proof, but it's as follows. Question, how many computable problems are there? Well, how many computer programs are there? Well, you save a computer program on a disk. The disk is made out of binary. You can think of that as a giant binary number. Okay, so it turns out the number of programs there are is countably infinite. So this is countably infinite. Okay? As opposed to that, how many problems are there altogether? Answer, uncountably infinite. Okay? Like the real numbers. There are vastly, vastly more uncountable problems than countable problems. Okay? So we've picked out 4 of them, but that's just the beginning of the story. There's much, much more. This picture is not drawn to scale. Okay, and I can't draw it to scale, but if I was to try to draw it to scale, it would be something like this. This is all problems that are uncountably infinite, and there's a few that are computable. Okay, very few. It's a small little circle that are computable. That's more like it. So, we started off with this thing saying, what can a computer count and what can a computer not count? What can a computer do and what can a computer not do? And the answer is a computer cannot do vastly more. What cannot be done by computers are vastly more than what can be done by computers. We've only pointed out 4 of them, but still there's a lot more that cannot be done. Okay, so that makes this the limitations of reason. Computers cannot do much more than what they can do. So that's an interesting point. Okay, Question. Now, this is section 6.4. We're not responsible for it. What's section 6.4? It says, you know what? What the hell is out there? Okay? And so I categorize, classify all these things that cannot be computed. So we can say a lot about those uncountably infinite number of problems that cannot be computed. We can start calculating some of them. Not calculating some, just classifying them, saying this problem is harder than that problem's harder than that. Again, this is not, you're not responsible, but it's a good read. I think you should read it. Good. The last section is called section 6.5, and that's more philosophical. And it asks the following question. Question. You ready? We saw that we can solve the halting problem for some problems. We also solved the zero program problem. We also solved some problem for printing 42 problem. We did solve some of those problems. So question, is our human brain better than a computer? I proved to you that computers can't solve them for all input, but what about the human brain? And the answer is, yes, we did solve them, but we solved for very small problems, okay, for very small programs. But larger programs, we would have trouble doing it. And I told you about this 10 minutes ago, about the difference between teaching an elementary programming class versus an intermediate programming class versus an advanced programming class. My brain cannot go that very far of telling when a program will go into a halt or not. I could do it for some, and I'm not the only one. So it's a very hard problem. Okay, other questions. So the question is as follows. Is the human brain more than just a computer? Okay? And a lot of people take this very personal, and if we were meeting in person, we'd be screaming at each other. And yes, computers seem to be somewhat limited, and computers don't fall in love, except in the movies. Computers don't feel like they're thinking yet. We feel like we have freedom. Computers don't seem to have freedom. So there are a lot of things that we think that computers are not as good as human beings. Okay? Okay, so computers don't have emotions. But question, do we really have emotions, or are we just programmed to talk about having emotions? Okay? And other things that are going on, your computer, you have the mind. The mind is what's that inner voice going on in your head. And then there's the brain. The brain is a physical object that's firing electronic signals back and forth. Question, is the mind something more than just the brain? Okay, they're clearly connected. Okay, if you drink tequila, you will not have a very good mind. If you take Benadryl, take a Benadryl, you'll fall asleep very fast. You won't be able to concentrate. I always tell my students, take an SAT. You all got into college, you had to take an SAT. Take a practice SAT while listening to loud music, and take a practice SAT while not listening to loud music. You'll see you'll get a much higher grade when you don't listen to loud music while you concentrate, because there are things affecting you. So your brain is being affected by all the inputs that are going to it. So yes, the brain and the mind are somewhat connected. I'd like to think that my mind is somehow more than just a physical device, but I don't know. Other people have thought about this question and come to different conclusions. I just want to bring up two people. Kurt Gödel, we talked about him. He felt that the mind is something more than just a physical device, and he was one of the founders of this field. He felt that the mind knows certain things about mathematics that the brain can never understand. Okay. Another person is a guy named Penrose. He's still alive. He's a mathematician. He's a mathematician, and he has this idea that somehow physics is more. The physics that the brain uses is not typical physics. It's some type of quantum weird stuff, and that's the reason why the brain seems more than just a mind. Okay? I'm sorry, the brain seems more than just a physical device. It's doing more because it's using some of this fancy physics. Okay? Next, a guy named Hofstadter, Douglas Hofstadter. He also theorizes about this, and he says something that we'll all like. He says, you know what? The brain can do some of that self-reference. Machines can't do self-reference, but the brain can do it, and maybe that explains some of the deeper things that the human brains can do. So because of the fact that a human being can think about what a human being's doing, can think about what a human being's doing, can think about what a human being's doing, can think about itself, that self-reference gives rise to consciousness and other strange things that human beings can do that computers cannot do. We saw every other physical device, because there's self-reference, there's some type of limitation, but Hofstadter says maybe there is no limitation. Maybe human beings are something more than just a physical device. Okay, then there's a whole discussion in this, and it's 3 pages, this last section. You are responsible for the last section. There's a whole discussion about AI, artificial intelligence, trying to get computers to act more like human beings. Okay, and people are doing this. And there's 2 things that I bring in. One is Watson, and I talked about him already. Watson is a computer that beat everybody else in Jeopardy. Okay, so computers are very good at language recognition and knowing a lot of data. And another one is Deep Blue. Deep Blue is a computer program that beats the world champion in chess. And so even the world champion of chess is now a computer program. So AI is pretty good. But like I said, there are certain things that computers cannot do, like beat us in tennis, okay, or fall in love, or have a moral thought and things like that. Now this section has a lot more questions than answers, but they're interesting questions and they're worth thinking about. So we are now finished chapter 6. We're going to do section 7.1 and 9.1, and then we're finished the semester. I hope you enjoyed it. I certainly enjoyed teaching it. It's a lot of material, but you have to learn how to write how to read those programs and tell different things about it. And again, these are all limitations of what computers can do. Not what computers can do efficiently, that we did in chapter 5, but what computers can do. Have a nice day.